Welcome back to part 2. Okay, you already learned what is PV equal to nRT. It is a ideal gas. However, at a certain temperature and pressure, this approximation might have a problem. For example, at high pressure or even at low temperature, this equation is no longer valid, and it causes seriously inaccurate because this equation, the calculation using this equation is independent of a species, and it is the same whether it is a single species or a mixture. The base is still PV equal to nRT. Okay, for example, at one temperature and a pressure, for gas A, the pressure could be too high. For gas B, the pressure could be too low. And for the gas C, it could be quite okay. So the difference between this A and B, C, is difficult for us to determine which one is correct, which one is not. So people tend to find the alternative way to explain this identity of gas. So we are shifting from an ideal gas, we are shifting to a non-ideal gas. Okay, bear in mind that it occurs at certain temperature and pressure. Okay, previously we learned the theory about a gas, the density and a volume affected by temperature and a pressure. And we have PVT relationship between, which is this PV equal to nRT. However, this assumption is no longer valid for high pressure and low temperature. Because of that, people find an alternative. Okay, not people, a scientist find an alternative. How to really calculate, how to really represent the gas property. So they came into a theory of non-ideal gas. So this non-ideal gas, or we call it as a real gas, it have three different equations. Okay, this is the first one. I don't know how to pronounce that. This is the first one. And the second one and the third one. These are the equation that we're going to take a look in this video. And as an alternative of using a lot of equation, they also came up with another alternative to find to solve for this non-ideal gas, which is they are using a compressibility factor and a K rules. Okay, we're going to take a look about these two things in this video. Okay, the first thing to introduce to you is a critical temperature and a critical pressure. As I mentioned previously, high pressure and low temperature, the PV equal to nRT is no longer valid. But how do we determine the high temperature is high and a low temperature is low, high pressure is too high? Because each of the species doesn't have the same property. So people came out with, again, people came with critical pressure and a critical temperature. So what are these critical temperature and pressure? The critical temperature in which a species can coexist in a liquid and a gas. Okay, I'm not sure how we can visually, but it coexists. It's not liquid, it's not a gas. So it coexists in these two phases. So at that temperature and that pressure, it is called a critical temperature and critical pressure. Okay. And then, so how well or poorly this equation of state is really depend on this critical temperature and critical pressure. The temperature of a system relative to a critical temperature and a pressure of a system relative to this critical pressure. Okay? And that is the key factor to determine whether PV equal to nRT is still valid or not. I bet I quite confusing you for this time, but don't worry, we just proceed first. And then a substance that have a temperature and pressure above than critical pressure and pressure, critical temperature and critical pressure is called supercritical fluid. Okay, because it above that. So the detail about this critical temperature and pressure, which is the detailed phases we're going to learn in the next topic, which is a multi-phase. So don't worry so much if you don't you are still blur with what I'm talking about. Okay, but here I want to tell you that this PV equal to nRT is really depend on this critical temperature and this critical pressure. Okay, let's go to the first equation of non-ideal gas or a real gas. Virial equation of state. This is an equation. It's more complicated than PV equal to nRT because it have additional term here. B, C, D, E, F, and until infinity. Okay, and it have a truncated version. Okay, the truncated version, which basically a simplified version, they took only until B. Okay, and then what makes this thing more complicated, because in order to find this B, you have to use another equation. Okay, for you to determine B, you need to calculate B0 and B1, and to calculate B0, you need another equation. Same goes with B2, you need another equation. And then another term here is TR. And this TR is really related to a critical temperature. There is another term. So this is quite complicated. And then we have here a centric factor whereby we can found at this table. Okay. This is the first. Okay, equation of state for non-ideal gas or real gas. Okay. So let's go to an example on how to use this equation. So in this example number 5, we have 2 gram mole of nitrogen placed in a 3-liter tank at a temperature of negative 150.5 degrees C. So you have to estimate the tank pressure, which is P, using ideal gas equation of state, meaning to say you can use PV equal to nRT. And then using Virial equation of state, the truncated version, the simplified version. And then you have to calculate the error. Okay. So we have here a nitrogen in a tank, in a 3-liter tank, at this negative 115.8 degrees C. And then how we know that the phase of this nitrogen are still gas, or it's actually have become a liquid, have turned to be a liquid. In order for us to determine that, we have to check on the boiling point of the nitrogen. Okay, so the boiling point of the nitrogen is negative 195. Okay, it's below than negative 115. So it is in gas form. So the first one, we're going to use PV equal to nRT. So again, you have to convert the unit from degree C into a Kelvin, and then you can get the volumetric flow rate, the volumetric flow rate, okay, the molar volume flow rate by dividing 2 gram, okay, dividing 2 gram mole and a volume, related volume here, and you get this value, and then you are using, okay, this one, okay, and then you can get the value of P. Okay, this value is when you use PV equal to nRT. Okay, the next thing to do is you're going to calculate the value of pressure by using a Virial equation of state, which is this one. So in order to solve for this, you already have all other value, but you have to calculate the value of V, which is using this equation. Okay, the first thing to do is you have to again go to this table B1. Okay, so this table B1 are really important for you to find the critical temperature and critical pressure. Okay, for non-ideal gas equation of state in this topic, you will take a look on this table B2, B1 a lot. Okay, so the first thing is when we have a nitrogen here, we go to table B1 and then we find the critical temperature and a critical pressure, which is, okay, this one and this one. Okay, and then you can start to calculate the value of TR using this equation, and then you calculate the value of V naught. Okay, just substitute the TR into this. Okay, and then you calculate the value of V1. Same procedure, but notice that they are different here and here. It's also here. Okay, another equation. And then you can calculate the value of B. And this eccentric factor you can get from this table. And you can calculate the value of B. Okay. Then come back to this Virial equation of state. You can determine the value of P. Okay. And last time when you are using PV equal to nRT, you get another value. And this time when you use Virial equation of state, you also get another value. So what are the percentage error between these two? So to calculate the percentage error, we are using this formula, okay, which is the ideal minus the true value. The ideal meaning to say the pressure that we get from PV equal to nRT equation. Okay. And then we get the error. Okay, just use directly, just use the equation directly. You just need to know how to get this information. Okay, critical pressure and a critical temperature you have to find from table B1. Okay, another two equation of state, which is a cubic equation of state or van der Waals equation, and another one is a SRK equation. It's more complicated than previously, and this is the theory behind, which I don't think you have to take care so much. It just you need to know how to use this equation. Okay. And then if you want to calculate a volume for this, if you want to calculate a volume using this SRK equation, it's using try and error procedure, and it's a very long procedure, which I don't include that in your syllabus. And the easiest way to calculate it, you have to use Excel, Microsoft Excel. You cannot do it manually. It's going to take a days to solve it, just for you to calculate the value of volume. Okay. And then let's go to another example. Okay, I might not giving you a lengthy explanation about this, but I want to introduce to you, there are three equations for non-ideal gas. The first one is a Virial equation, the second one is a the Van der Waals equation, and the third one is SRK. When you in your lab, you're going to use a software called HiSys, and this equation of state are really there in that software. You just use it later on, and that software will solve for you. Okay. And for the next example, we're going to see how to use this SRK to determine the I cannot remember the question. Let's go to the question. Okay, so we have this. Okay, we have this equation. So we like to estimate the pressure. Okay, the SRK equation you can use to calculate a pressure, a temperature, but for a volume, it is a try and error method, just for volume. Okay, so when we have this equation, okay, and you have another equation to get the value of A, to get the value of B, to get the value of alpha, to get the value of M, and to get the value of critical temperature. Okay, the first thing to do is you can determine the value of molar volume. Okay, whereby this one. Okay, that's the first that you can do. The next thing to do is, again, you have to go to table B1 to determine a critical temperature and critical pressure for carbon dioxide. Okay. Oh, I forgot to read the question. Okay, we have a gas cylinder with this volume and this mole of a carbon dioxide at 300 Kelvin. So we're going to use SRK equation to determine the gas pressure. So the next thing to do is you have to go to table B1, and then you can determine the value of critical temperature and critical pressure so that you can get the value of A, right? Then you can also get the value of B because it's using critical temperature and critical pressure. Okay. From there, you can get the value of M because you only need this table. Okay. So this table will help you to determine the value of M, okay, which is you are using this eccentric factor. Okay. And then the next one is you're going to calculate your TR because this alpha use TR, you get the value of alpha. Okay, once you get the value of A, B, alpha, temperature, gas constant, B, volumetric flow rate, volumetric flow rate, you can get the pressure. Okay, so these are the thing about equation of state. Okay, I might not really explain in detail what is this equation and why is this, why is minus, why is this. It is because it's not at your level to really understand how you're going to derive this, why here we have plus, why here we have minus. You need to think so much about this. It's just for you to know there are three equation of state and how to use it. It's simple. You can get all the parameter, you can get the value of critical temperature, critical pressure, and you can calculate the value of pressure. Okay, and the last topic to be covered is a compressibility factor. Okay, previously we have PV equal to nRT, but here we have PV and we have another term here, Z. Okay, so this Z is equal to 1 for ideal gas, but because of a non-ideal gas, which is at specific temperature and a pressure, that gas not behave as a ideal gas, it will behave as a real gas. So the equation become like this. Okay, so the alternative is this one. Okay, as you can remember, V is equal to V over N. Okay, I don't know what we call this, really forgot. And we can get the value of Z, which is a compressibility factor. Okay, and then from we also can calculate an ideal critical volume, which is using this formula. Later on you will see why we really need to calculate this critical volume. And then for a hydrogen and a helium, when you get the value of critical temperature and critical pressure from table B1, from table B1 you can get critical temperature and critical pressure. You have to do a correction, it's called Newton correction. You have to add 8 Kelvin. You need to add 8 Kelvin to the critical temperature, and you have to add 8 atm for the critical pressure, and it is only for nitrogen and helium. And then you have to calculate your reduced value, which is TR and PR, by using this equation. Okay, and then the value of Z can be determined from this chart. Okay, this is called generous compressibility factor chart. So these are the steps what you need to do. The first one is you have to look up at table B1, find the value of critical temperature and the critical pressure, and then you have to calculate a reduced value, the value of TR and PR, and then you can find the value of Z at this chart. This chart have a few with a different value of Z, a different range value of TR, and different value of PR. Okay, notice here in x-axis it is PR, in y-axis it is Z, and the line represent a reduced temperature. This is another chart. This is another compressibility chart whereby the value of TR here is 5, and there is another line here which is the value of molar volume. Okay, and additional parameter having their own line, so you can find the value of the compressibility chart based on either PR or TR, or you can use the value of PR coupled with the value of volume, molar volume. or the value of molar volume coupled with the value of TR. So you need only two parameters to get the third one. Okay. And the steps are the same. Same goes with this one. Different value of TR and PR. Let's see one example. In this example, there are 100 gram mole of nitrogen contained in 5-liter vessel at this temperature, negative 20.6. So we want to estimate the pressure inside that cylinder. What you need to do is we start with table B1 for nitrogen. We go and find the value of critical temperature and critical pressure, which is this one. And then you have to change your temperature into Kelvin, change the unit of pressure into Kelvin. Then you can calculate the value of TR. Then you can calculate the value of VR, which is molar volume. So you have these two values. Okay, you have this and this. Okay, so you can look up at the chart, not the chat. Okay, so at the chart you can see. Okay, I really hope that you can see it clearly and try to zoom it. Okay, and from the chart you can determine the value of T, and using this formula you can determine the value of P. Okay, I did zoom it for you, the chart, whereby in this yellow line it is the value of TR, and then this green dotted line is the value of VR. When you have TR and VR intercept each other, you can find the value of P, and you can substitute into the formula. Okay. It might be not so accurate, but it is an approximation. And I'm sorry that I couldn't have any more clear chart for you because I cannot redraw this. Okay. Last time I retouch everything for the calculation and everything, but for this chart I cannot draw it. Okay, how about for the non-ideal gas, which is involve a mixture? Okay, when it's involve a mixture, we are using K rules. K rules estimate that pseudo-critical property of mixture as a simple average of a pure component critical constant. It's okay, you don't have to memorize that. It's enough for you to understand that you need to use this equation for a critical temperature, this equation for a critical pressure. Because of this system having a mixture, you can see here a mole fraction of A, a mole fraction of B, and a critical pressure for critical temperature for A, critical temperature for B, or C, or any other. Okay, that's why we have this three dotted line. Regardless how many mixture you have, how many species you have to go and find each of the critical temperature and critical pressure for each of the species, and then you sum out. Okay, and then the Z here becomes ZM because it is for mixture now. Last time it is a single, but this time it is a mixture. Okay, and then Y is a mole fraction. Okay, so how to use this? Don't think too much. I'm just showing you directly how to use this equation. Let's go to our last example. Okay, in this example, we have a mixture of hydrogen and a helium. In this example, we have hydrogen and nitrogen. contained in a tank at this pressure and the temperature. So we have to estimate the specific volume, which is V, okay, for this mixture using case rule. So the first and most important thing to do is go to table B1. Okay, go to table B1, find a critical temperature for nitrogen and critical pressure for nitrogen, and next for the hydrogen. Okay, remember that for helium and hydrogen, you need to do a correction. You have to add 8 Kelvin and 8 atm for the critical temperature and critical pressure, and then you can use this pseudo critical constant. Remember this formula last time. Okay, we just substitute all the value. Okay, the mole fraction time a critical temperature plus another mole fraction plus another critical temperature, we get this temperature. And then same goes with pressure. Oh, this is a typo here because I forgot to correct it. Okay, for critical pressure, same. Okay, then you get this value. So you need to further by calculating the reduced value, which is the value of TR and PR. Okay, notice that for a single we use TR, for a mixture we use TR with apostrophe. Okay, so you have the value of TR and PR. You have two parameters. So you can take a look at the compressibility chart. Okay, for the value of PR here, we go straight away to the line. Okay, and then we go to the line of TR. Okay, so I did zoom it for you. Okay, for the value of TR, we go to the value we go to the value of TR because the value of TR is 3.2. There is no deadline, but we can estimate around here, and then we can get the value of Zm. Okay, when you get the value of Zm, substitute into this equation, we can get the value of specific volume, or I'll always say it as a molar volume. It is the same because this one is called specific volume, or I always call it as a molar volume because it is a volume divided by mole. Okay, and with that I end up this topic with this compressibility chart. Don't get confused with sometimes I mispronounce the term, but you just need to identify what are the parameter, what are the value are really needed, which is it is a volume, it is a temperature, or it is a pressure, or even a mole. But based on all the example, the three common value that we're looking for, which is a temperature, the most common value that the question asks you to look for, which is a pressure and a volume. Okay, and all these examples showing you on how to apply this equation. Okay, for your level, you just need to apply this equation based on the instructed by the question. Okay, the question should ask you whether you have to assume it is ideal gas or non-ideal gas, or what kind of equation of non-ideal gas that you need to use. Okay, I will just give you a simple equation, don't worry. Okay, so see you later in next topic. Thank you very much.